Okay, I think we're live. Good morning, afternoon, or evening to everyone, all our listeners. I'm James from DoraHacks, and welcome back to another episode of our Space Tech Workshop series. Today, our guest is Cathal Mooney, who is materials engineer at the European Space Agency, ESA. Just for those who don't know too much about DoraHacks, let me give you a quick introduction. DoraHacks is a leading global hackathon organizer and developer incentive platform, and we love supporting innovation in the areas of blockchain, quantum computing, space techs, and other frontier tech fields. To date, we've supported over 20 early stage projects working in the space sector with our ongoing long-term space resources and exploration grant. So everyone building within the space sector is welcome to participate and receive support from us. And another big initiative I just want to mention is our Starship Use Cases Hackathon with over 100K dollars in prizes. Considering the vast potential of space exploration offered by Starship's lift capacity, we've got over 20 use cases and open challenges for hackers, including an orbital hotel, space-based farming, routers for global Internet of Things, metals from the moon, etc. So this hackathon is live at the moment, and we aim to motivate all space enthusiasts with engineering skills to build their solutions for space by taking part. The links for that will be in the description, and we'll touch again on it later. But let me then hand over to Cathal Mooney, again, materials engineer at ESA, who'll be doing a presentation today on the topic of materials design aspects for a lunar habitation. So I'm sure we're all very eager to hear what Cathal has to say on this, and so I'll hand over to you now, Cathal. Hope your microphone is unmuted. Go ahead.
Okay, thank you for that, James. I hope you can hear me.
I can hear you loud and clear.
Okay, thank you for that. And good afternoon, good morning, and good evening, everybody, depending on where you're logging in. I wanted to give today an overview and a description with respect to materials aspects for lunar habitation. This is primarily focusing on the design aspects for structural materials and also for inflatable materials that we have for potential use for habitation on the lunar aspect. I want to talk very briefly initially with respect to the section and where I am coming from in the European Space Agency. I'm a materials engineer there for many years, now for 17 years, and part of my project support is for human-rated projects, most notably for the Orion, the Artemis program with MPCV, where we are involved at the European side for the propulsion and the ESM, the European Service Module, and also with respect to the new development for Gateway. So we have a huge involvement with the habitable station that will be coming to fruition in the next few years, and also with respect to the lunar aspect, we have also a current project which is called the Prospect project, and it's the lunar mission for the South Lunar Pole, looking at ice volatiles and looking at the extraction of samples in relation to ice volatility and looking at volatile extraction from that. So there are current projects that the European Space Agency is involved in. Me, myself, I'm a materials engineer, so I'm looking from the materials aspects, and our group is involved in looking at many aspects of materials and process engineering. I'm aware that there's people with varied interests and areas of support and support topics. So if you have any questions, certainly do pose them at the end, and we'll try to get through to them. Just to give you an overview of what our section is, I'm coming from the Materials, Physics and Chemistry sections, which is part of ESA, which is part of the European Space Technology Center, which is called ESTEC. So we have about 2,500 engineers in total. And there we have the central hub of the research and the development for what ESA is. So we look at developing the missions, we look at developing the materials, and in our case, we look at materials and process engineering and aspects for all of the different missions, the science missions, the research missions, and indeed innovations in new materials. So what we have here is just an overview. You can see a map here of ESTEC. So this is in Noordwijk in Holland. And that is there for many years. ESA itself celebrated recently the 50th anniversary, and then the site is many years on site, and we have about 2,000 people on site. Our mission in the materials, physics, and chemistry section, we look to have a center of competence, and we look for aspects in relation to the chemical and physical characteristics of materials and related processes. So we look at all aspects from concept to mission development, all the way through to materials and process qualification, through the different design phases of the engineering milestones, the PDRs, the CDRs, and up until mission and flight acceptance reviews. And then we also look going on at the materials aspects in relation to in situ exposure testing. So we do things like accelerated testings. We do things like looking at the space environments. And we have people then from various aspects, contamination engineers, we have physicists, we have physical chemists, organic chemists. Me, myself, I'm a materials engineer. But we have people then from all different aspects, contamination engineers, aeronautical engineers. So we have a huge range of people coming together to support the materials and physics section. So it's quite a broad range. This is just giving a look at one of the aspects and looking at one of the mirrors for the missions that was flown some years ago. And here we have the group using UV light, the black light, to look for contamination, and certainly particulate contamination for contamination sensitive surfaces. So this is something that we do and is one of the key aspects for mission involvement. Now, the main core activities of our group, which would be Tech QEE, under the materials group, would be cleanliness and contamination. We look at in situ materials, space environmental testing, and also qualifying materials and processes for space qualified missions. So where we have aspects of extreme temperatures, where we have aspects, say, of low temperature or extreme temperatures, say for the solo mission going to the sun, or where you would have extreme lower temperatures, for instance, the Bepi Colombo mission going to Mercury. We had to qualify materials as low as minus 180 and up to about 230 degrees. So you look for the whole range of materials that are space environmentally tested and qualified through those temperature ranges. So it's not a simple thing with respect to choosing any material. You have to choose something that is heritage of the supplier, of the material, of the process, and that it is fulfilling the needs of the space environment. In this case, extreme temperatures, radiation, the space environment, and what the function of the material is. So that's what we look at within the group. There is all our happy faces. So happy workers are productive workers. So I'm hiding here in the back somewhere. And then we have Ricardo, who was before the section lead. Now Gosha is section lead that is there. And we have some of the instrumentation. You can see some of the in-house instruments that we've built for in situ testing. And these are certainly unique pieces. They are not COTS items. They are not facilities that you can buy commercially. They have to be designed, and they take many years of engineering and heritage to come up with those. So they are some of the equipment that we test. I'm just giving an example here of one of the facilities that we use. This is called the STAR facility, which is an in situ space environmental test for exposure of materials. So here in the top facility, you can see it looks at UV and VUV, extreme ultraviolet, vacuum, and thermal. So we also have particulate radiation, which is the electron and proton induced radiation testing of materials. And on the bottom, we have an example of the LEOX facility, which is simulating the low Earth orbit, where you have an increased concentration of the oxygen concentration, and you have the atomic oxygen phenomena where materials are eroded on the surface because of that. So we simulate things like plasma-induced aging, plasma-induced effects, atomic oxygen, and materials aging. So we look at in situ testings, and here on the top facility, you can see this one here, the STAR. We can actually do in situ testing. So that's something that we are acutely aware of, that gives us the real life picture of materials and processes when they're exposed to space environments. And that's all leading into the presentation that I give here today on the lunar aspects and what is needed on that. This is just an overview of our activities for some of the physiochemical characteristics. So we look at gravimetric analysis, some of the thermal aspects, thermo-optical characterizations, microscopy, surface analysis like SEMS and X-ray tomography and different aspects like that. And then on the chemistry side, with respect to the species and what are there, of course, the standard infrared. So FTIR can be used for chemical identification. Gas chromatography, mass spectrometry can be used, and then there's the various other spectrometers of X-ray, photoelectric spectrometry, Raman spectrometry, and SIMS. It's also some of the equipment that we use. This is just giving a small overview here of some of the development in the areas that we look at. So we look at, for instance, nanovation and new coatings for extreme environments. So these are some of the coatings where we looked at radiation-resistant materials, high voltage materials, for instance, high temperature potting adhesives is an example of some of the materials that we use. And there's also been recently a development of the European QCM. So this is for contamination analysis, where we look at the quartz crystal microbalance, and this has been used and qualified specifically for space use. So this is something that our group does. As well as that, we look at modeling. So you have fast contamination modeling using the modeling tools for molecular contamination. We have that on the top right here. And then we also have various facilities where we look also at in situ materials exposure testings. Here in the middle, we have examples of some of the thermal control materials for different absorptivities between reflective and absorptive materials, depending on what you want to use. So we have a whole aspect of the various materials aspects between testing, between sensors, between tools and various capabilities. But it's just to give a small overview as to what we do and what our capabilities are. This is just giving an example here of one of the facilities called the Cross-1 facility. And this is used to look at the exposure of materials under space environments. And I show you here the example of the Bepi-Colombo solar array assemblies, the SCAs, where we used the exposure of the materials on CFRP. So this is a composite backing. And we were looking at various aspects of the materials under and simulating the Bepi environment. So when we talk about, for instance, going to Bepi-Colombo and what it is, we have extreme temperatures. We have 20 solar constants. So in this case, it was 13 solar constants, 12 solar constants that were used. So we can simulate environments like that, where we have, for instance, the lunar environments. Of course, we can have dust facilities. We can have lower temperature facilities for the lunar nights. And then we can have the in situ radiation simulation as well. So all of these facilities can be built, and we have the capabilities to build those to simulate various environments. So that's just giving an example there of the cross facility and what is there with respect to pressure ranges, the outgassing with the QCMs, and then the accelerated testing as well. So that can be done as well. And this one here is just another facility called the STAR and the STAR 2, where we can look at in situ measurements of thermal responses using the IR cameras. So we can look in situ at the degradation of materials, which is very, very beneficial. And here we could look, for instance, also at the behavior of the radiation. So you could have radiation with the temperature and with the high temperature environments and the vacuum to look at the degradation on the surface of the materials. So that's really what these facilities are doing. So just to bring everybody along, today what we are looking at are what it means to go to the moon. What do we look at with respect to the aspects of that? And what I want to talk to you about is the aspects in relation to the environmental aspects, the materials aspects, and the safety aspects and the challenges for going to the moon and what that means. So when we take the environmental aspects, of course, we're talking about the lunar habitation. So we have aspects of outgassing for the materials. We have a temperature range, most probably in the range of -200 to 90 degrees. And then we have thermal cycling of materials. So we have to look at the aspects of thermal cycling and what it means for the materials functionality, what it means for stresses, and what it means for the choice of materials when you're choosing materials for a habitable environment. Of course, the radiation is always something that you have to take into account. So you have the ionizing and non-ionizing radiation, be it between the particulate radiation and interaction with materials, or the UV, which is the non-ionizing, and what that means with respect to functionality of the materials. When we talk about the lunar aspects, of course, the most probable thing is the dust. And here we have things like the issues of dust erosion, micrometeorites, and what that means for a choice of materials. If you have an anti-static material, if you have something with natural dust repellent, or how you actually choose your materials with respect to materials and dust interaction. On the top right, I have just some of the issues that are looked at. So for instance, the design and the launch loads have to be looked at, the radiation and the thermal control, structures and the structural issues with respect to the materials, and then the long-term aspects like creep, fatigue, and degradation, and what it means for materials compatibility. And on the safety side, on the bottom right here, we have issues then that need to be looked at for the internal materials. So these are the materials in the habitable structure that, if you see here on the main schematic, we have the internal structures where you must take into account issues like flammability, off-gassing, toxicity, and fungus. So these are aspects where they're actually associated and in direct contact with the crew. So you need something that's functional, you need something that's safe, and you need something that will not induce any hazards either to the structure itself or indeed to the crew. So this is an example of the schematic that's taken from the report, a report that we did some years ago called the Moon Village Report, and this is from SOM, one of the American architectural societies, and this was a report that was done with the Massachusetts Institute of Technology and ESA as well, so in relation to the feasibility of choosing materials for a lunar habitat. So this is just giving the breakdown of the structures and what it means. Now, there was various aspects of this report that was looked at. We had the main structural design, which was using CFRP structures and also titanium for some of the more rigid structures. What I'm talking about today is maybe just the outside ones. So it's the inflatable materials and the organic and the lightweight materials that are there. So that's the focus of my talk. So going on, to give an example just of the space radiation, of course, we're all aware of the aspects of space radiation and what it means for lunar habitats in particular. So one of the key aspects and findings of the study was the issue of the radiation-induced damage. So there is for sure high amounts of radiation there. You have, of course, a mix between the ionizing and non-ionizing radiation. So here you have the example showing the X-rays and the ultraviolet into the ionizing region here. Of course, you have the gamma rays, and then you will have the alpha and beta. You will have the electrons and the particles, protons going on from that. The non-ionizing, of course, will be the UV and what you have on that side there. So there are aspects that need to be taken into account when looking at building habitats, when looking at spacesuits, and looking at the various design aspects that you have in mind. So you have to take into account, of course, the outside environment, galactic cosmic radiation, trapped radiation that you have also present. And then you have solar energetic particulate events, which are SPEs, which are giving high induced energies of radiation. And of course, then the constant UV and VUV radiation that you have to take into account. This is just showing an example here of some of the radiation, the dose effects. So this is something with respect to the exposure of radiation and what it means. So when we choose materials, what we're actually looking at is we would take, for instance, something like a lifetime of 20 years. So if we take, for instance, the gateway, what would be there for a mission of 15 to 20 years, we would be looking then at the higher dose levels. So you would be talking here about 1 by 10 to the 6 up to 1 by 10 to the 7 rad of total ionizing dosage. So these are something where you need to take that into account with respect to the upper ranges, specifically for organic materials and what it means for functionality and degradation. Certainly for some of the polymeric materials, of course, 10 megarad and that type of thing is a threshold. You can get higher for some of the more cross-linked materials, but then for some of the more benign ones, of course, yeah, you can have effects where the organic materials are indeed starting to break down because of the radiation effects. So you can get things like thermal control degradation, you can get structural strength reduction, and you can get a yellowing, or you can get a breaking of the polymer as you expose it more to the radiation. So these are things that need to be taken into account when you're designing and choosing your materials. So going on from that, so here's just an aspect looking at the proposed design that was for the habitable structure on the moon. So here we were talking in the Shackleton area on the south lunar pole. So this was somewhere where you have maybe a little bit more of a radiation shielding in some of the parts that were there. But in saying that, the proposed way forward for some of the designers on this was to use the option of a regolith shielding, and this was to use in situ resource utilization to build around the structure. You can see it in the middle, to build here something that was, say, radiation protection and radiation-induced protection that was there. This was something primarily for the crew protection. Certainly, it was found that if you had a structure like that, where you had a vertical structure, certainly it was found that this orientation was a little bit more exposed to the radiation. But even at that, it was proposed that the lower regions, you would have a regolith shielding for the crew, where the crew would be then in sleeping quarters on the lower regions, and they would be protected from the radiation. Water is also mentioned there, and that is something for one of the options that we looked at for the layering and textile effects, for the different layering effects of the shielding and what was used with respect to the crew. The tables that I show there are generic tables with respect to textile fabrics and what is there with respect to some of the breakdowns. So you have insipid to mild, mild and moderate, depending on your radiation dosages. And here you have 10 to the 5, 10 to the 6 gray for the dosages. And again, here you have 10 to the 6, 10 to the 7, where most of the polymers can do that. If you look at this, you see the higher ranges for the polyamides, the liquid crystals and the polyethers, so the PEIs, things like that, have quite radiation resistant effects. Lower down on the bottom of the scale, of course, you have things like POM and PTFE, which are slightly lower with respect to the radiation tolerances. So there are things that you have to take into account. Going on from that, looking at the environmental and the temperature aspects, of course, for the lunar, we have ranges most probably in the range of -200 to about +100, 125, 150, that kind of range. That would be the nominal lunar day. So you have to take and look at aspects then when you have the hot and the extremes, what it means for that. And certainly where we have a habitable structure, where you have structures that are slightly under pressure, where you have a tensile force of that, certainly you can have aspects, for instance, like viscous flow and creep and strength reduction. So this is where we look at, for instance, the exposure to constant loads and what that means with respect to the materials aspects. So certainly things like the windows, where you would have acrylics that would be used, polycarbonates, things like that. Yeah, you could get sometimes a creeping effect from that, depending on the loading and the structural capabilities that are there. And certainly strength reduction is something that you have to bear in mind. So here I have written that with time and with loads, the ultimate tensile stresses can in some case reduce to a factor of about 50% from the original over a 20-year period. And then the thermal cycling and things like fatigue, debonding, and radiation accelerated effects all have aspects and can contribute to the degradation of materials. So there's something that you have to bear that in mind. And the lower ranges also considers, as I say, the challenges for space environments and things like issues like the potential of loss of properties, becoming brittle, or indeed not being able to withstand strains or the actual sustained load has issues on it. And then I also mentioned here, say, debonding due to CTE and what that means with respect to materials choices. So for all of these aspects going forward, you have to look at the various aspects. Radiation is one, temperature here is another one with respect to materials. So you have to ensure that the materials are qualified, that they meet the synergistic needs of the radiation, the temperature, and the environment. And there is where we come in with some of the facilities I mentioned at the beginning. So I'm just going to take some water. Going on, what we look at here are some of the choices with respect to the materials and what can be used for, say, thermal balance. So this is one of the aspects when you're choosing materials, whether you want an absorber with an absorbance of a high absorbance or something where you have high emittance. So depending on what you need for the thermal balance between a total absorber or a total emitter, or a balance between the two, you have the various aspects of that. So depending on what you need, for instance, an OSR is on the bottom, you have an alpha to epsilon ratio of 0.09, so actually quite low. So you have a high emittance and a very low absorbance. And then in the middle, of course, you have, for instance, some of the paints, like a PUK paint, or you can have a white silicon paint, depending on what you have between the absorbance and the emittance, and what that means for your thermal balance and the functionality of thermal control. So going on, I'm just showing just some of the examples here. For instance, for black Kapton, that can be used for long-term missions where a low aging effect in the surfaces are needed. Or for instance, you could use a double-sided alumina. So depending on what you need for your alpha epsilon and what your thermal control functionalities are needed, you can have a whole range of materials that are needed for that. Of course, bearing in mind for all of these, for a lunar habitat, you're going to have radiation and you're also going to have dust. So the design aspects with respect to whether it is a conductive material or not also has to be borne in mind. So do you have something that's naturally repellent with respect to electroconductivity and with respect to a charging or a dissipation of the dust, or indeed where you don't have that, what does it mean for thermal control with respect to the addition of dust contamination on the surface and what that may mean for the thermal balance of the materials that you use. So they're all aspects that need to be looked at. What I show in this slide here is just a breakdown of some of the launch activities. So this is something from going through to the testing phase, to the transportation, to the launch, to the commissioning, to the mission itself. So it just gives an overview of some of the issues for the challenges and the needs for materials and what is needed on that. For instance, for testing, of course, off-gassing is a main requirement, and off-gassing is the toxic off-gassing or the release of toxic compounds under a pressurized environment. So there you would have to choose materials which would be low in off-gassing, so you don't have a toxic effect or some kind of a synergistic effect to the crew where you can induce a toxic response. The inflatability on the inflatable sector needs to have leak testing, so you need to be able to leak test the actual structure when you're there. So that is actually a challenge with respect to the interface between, say, a rigid aluminium or a CFRP and the inflatable material, and what it means with respect to the interface, how you're qualifying the interface, do you have a leak-tight structure, and what that means. And that has many aspects with respect to the testing, with respect to the design, and also with respect to when you are launching the structure itself, what it may mean to inflation during that time, what it may mean during the actual mission itself. So here, for instance, during the launch phase, you can see that the ranges, the non-operational ranges for that may be in the range of -100 to +100. So that actually induces challenges in itself with respect to the fabric materials, with respect to the inner bladder materials which are used, and what that may mean with respect to inflation, with respect to stresses on the interfaces and things like that. So when you're designing materials, of course, you have to take that into account. Do you have something where you have pores, or where you have the release of air or trapped gases inside, or do you allow for something that is actually needed, and then it must sustain then under a sealed environment the environments of the launch, and what that may mean with respect to loss of pressure and the vacuum facility. So they're all things that has to be borne in mind. Going on from that, of course, the concept of the operation, the ConOps, we looked here at various aspects. So we'd have, for instance, docking and the transportation of the vehicle. We would have the landing. So once you land and once you're there with your structure on lunar habitat, what it means, deployment from the lander. These are all aspects that need to be taken into account. Transfer to the building site, assembly of the architecture, and then inflation. So the inflation is a point again where the materials come in, because you are inflating the material under cryogenic temperatures. So again, here issues of the structure and issues of the materials choice come into play, because, for instance, some of the materials may not be foldable, they may not be flexible, and certainly where you have air constraints, as I say, in the bladder material, then there is a potential then for additional stresses. It may need to be heated to induce or to release a mechanism, and there are certainly aspects that need to be borne in mind for the operational part of that, and that's the inflation aspect of the ConOps. There's also things like the outfitting, the installation, the unoccupied phase. They're all aspects that need to be taken into account. We can't just go to the moon and expect the stuff to work naturally. We have to take crewed, uncrewed, occupied, non-occupied, and the various aspects of use and of maintenance of the material. So they're all part of the materials choice and what we look for. Certainly in the unoccupied phase that is here, there is the prolonged risk of induced stresses. There is a reduced flammability risk, of course, at low pressures and the lower oxygen environments. But certainly during the occupied phases, then certainly those aspects have to be looked at as well. So this is just giving an overview here. We have a schematic of some of the rough orders of magnitude of the mass that was used. So we have various figures here that are used. Certainly when we were looking at the materials aspects of the habitable structures and what was being used, if you look here on the far right, the target then and what was there for the achieved densities, there's a huge order difference between those. So when we did the calculations for the moon habitat, certainly the target density for the materials was in the order of 9 grams per centimeter squared. So this is something where we were looking at materials with that kind of density and with that kind of capacity for radiation shielding. When we did the calculations, and I show you some of the sheets later on, we were getting a value of about 1.7, yeah, or 2, close enough to that. So there is a factor of about 4 in relation to the materials and the current state of the art that is used for habitable structures, and indeed what is needed for protection and adequate radiation protection of a crew during a period of, I think, 3 years. I think that this was a 3-year mission that this was based upon. So we're talking about south lunar radiation. We're talking about the crew-induced radiation protection for that. And there we see that taking the structures and taking this into account, we needed to have a figure of about 9. We were getting about 1.7, as I say. And then the target then for the shelter, if you look at on the bottom line just under that, the target for the shelter is about 25 grams per centimeter squared. So here we're looking and basing the calculations then for the mass figures on that, taking aerial exposures and taking the main inflatable area into account. So you can see when you do those calculations that you're getting potentially a mass of the current mass for inflatable materials alone of about 6 tons. So these are things that need to be borne in mind. We have that under some of the figures here on the left, where we look at the overall mass and what is there. So you see the structures, of course, was like in the order of about 30 tons. The life support system, the ETLIS system, was about 10 tons. And then you have various thermal controls, harnesses, and then you have powers and mechanisms and things like that. That's not taking into account, as I say, some of the materials aspects which are there with respect to the figures on the right. But even taking that into account, with the dry mass, you have an order of about 50 tons of dry mass. For the systems, including that, you put another 10 tons on top of that. So in dry mass, including the systems, is about 60 tons, giving a net wet mass of about 70 tons. So you're talking then all of a sudden with respect to the capacity of launchers, what it means for payloads of that size, and what is the capability with respect to launching if you want to get to a lunar environment, and then what it means with respect to the choices of materials and what is there. So this is some of the figures and the aspects we looked at for that. Going on, what we have here is just some of the examples. This is the Bigelow. I think everybody is aware of that. So it's the beam Bigelow expandable activity. So this is showing some of the development that was used for the ISS. And you see here at the bottom right, some of the deployment of the Bigelow structure. So this is something where you have a semi-rigid structure on a ceramic or a fabric material. Of course, the Bigelow was attached in 2016. In 2019, it was certainly first assessed and it was certified from the beam company. And it is commissioned there until 2028 or 2030, depending on the end of life of the ISS. So it has exceeded performance and it has exceeded expectations with respect to functionality and use. The materials that were chosen on that, of course, it's proprietary, but of course, the main drivers of that were radiation-induced materials, lightweight materials, and then materials that were able to sustain the vacuum and the thermal environment. So we take a lot of some of the design aspects that have been used from the Bigelow and what is being used in that. So I think it's a great example of some of the engineering and some of the science design that was used for habitable structures, and it's certainly a novel design. Going on, here's just an example of some of the Italian structures that were built by Thales Alenia in Italy under the ESA commissioning, and we have some of the examples of the inflatable modules, the IMOD, and certainly here on the left, you see some more examples of capturing mechanisms. So these were things that were developed over the years. It's still coming around again with development and what has been used. Certainly these were 2010. There was some examples of inflatable capture mechanisms, of IMOD, which is the inflatable manned module. So that's here. And then the Flex, which is the flexible expandable commercial module. So there's some of the colleagues in Thales Alenia. The point of contacts are there on the bottom right. Certainly, if anybody is interested, they can come to me again, or certainly we could give information to the contact point in Tallasalenia if there was interest in that. Of course, with all of these, you have the main design aspects. You have the bladder, structural restraint, the MMOD protection for the external factors, and these are the main ones. You have it in the Biglow, you have it in these as well. So these are ones that were actually chosen and looked at for qualification and went through some test phases many years ago. So certainly there is heritage also on the European side with respect to design aspects of that. Going quickly on, I'm aware that we're going through time. We have still some more slides to go, but these are just breaking down the habitable structure between the external and the internal. So this is the external layers of choices of materials for a habitable structure. So we would look at the vacuum externally exposed materials. When we look at these, just for the external structures, of course, the main one facing out towards the lunar habitat, we would have deployment systems, for instance, straps that would be used to maintain it. And then we could have an optional layer of an external layer, for instance, using Nextel. Yes, so this is an aluminosilicate, and it's a boron oxide that is incorporated to use for protection against lunar dust, against the radiation, and against that environment. Going in slightly further into the structure where it is, of course, for conductivity and for mitigation against dust and ESD protection, you would use something like an MLI, where you would use a DMA, which is double aluminized mylar or double aluminized kapton. Also, black kapton or stamet could also be used for these internal structures to get to have choices on ESD, to have choices on thermal behavior, and to have choices on dust contamination. Going in further into the structure, of course, you have the fabric of the MMOD, you have Nextel, and then you have foams. For instance, low-density polyurethane foam can be used then for the structure of that. The restraint layers, which I showed on the previous slide, of course, we could use materials like Xylon, we could use Kevlar or Nomex, depending on what is there. So they're well-proven materials that are there, that have been qualified, and of course they are used for structural restraint layers. This is an example. I'm just going to take some water. This is an example here of some of the foams that are being used and some of the materials for those aspects. So, okay, these are generic polymeric materials. You have the creep resistance of Vectron, Dacron, Kevlar. They're the generic materials. The foams, of course, on the inside, you would have things like polyurethane foams, where you would have lightweight and you still have the rigidity of the structure. So you have on the bottom the aspects of the cost and then the generic properties on that. This is an example here of Kevlar. It's a well-known material. It's heat-resistant material, liquid crystal, and it's a synthetic fiber. So you have high toughness, high strength, high modulus, and good thermal stability. So you have a good range of working properties for more extreme environments. And this is the Vectran, of course, quite a new material as well. It is compliant to the outgassing, so certainly under the ASTM testing for outgassing, it complies to that, so you don't have an issue of cross-contamination. You have good strength, you have good resistance to flammability, you have good creep resistance, so it's a good material that can be woven for the outside of the material and the structure material of a habitable inflatable material structure. And this one here is Nextel. Of course, Nextel is well proven because of its heritage as well. It was used before on the space shuttles for the re-entry. And of course, today, Nextel fibers are used in high temperature applications, for load bearing applications, for blankets, and for different high temperature functional materials like that. So it's certainly used on the underneath, say, of the launchers, where you have high temperatures. This is a standard aluminosilicate boron oxide material. You have various ranges of that. Then, and because of the glassy phases and the crystalline phases that are there, of course, you have higher temperature capabilities of it. It is a ceramic material, and it is high strength, and you do have the good thermal control, of course. There you see the absorptivity and the emissivity of that. With respect to the functionality for the long-term exposure, of course, yes, it's also good. So it's a good all-round material to be used. Going in, so this is the inner layer. So this is the internal pressurized side. So this is, of course, in context and in contact with the crew. Certainly when you're looking for those materials, you want something that has air containment. So certainly it can't be something that leaks air. It has to be something that you have a bladder containment, for instance, that you don't have any issues of transfer or diffusion through those layers. And of course, being internal, you have to have the general issues, for instance, with respect to flammability, with respect to toxicity, and what that means with respect to materials choice. So here you have the various breakdowns of the layers, the air containment, the bladder separation. We use aramid. The bladder itself, CPAC was used, which is a relatively new material that was used on the Bigelow. So it's a mix between nylons and polyethylenes. And then, of course, the inner material, of course, for the separation layers, and the inner material with the crew and with the habitat area would be Nomex. So that's for protection as well. So, of course, all of the aspects there with respect to safety, flammability, functionality, and with respect to oxygen limits have to be borne in mind for materials choice. This is just an overview here of some of the inflatable structures. It just gives you an example of some of the materials design choices and what was there and what we look for. So when we're looking at these aspects, we have to take water resistance into account, oxygen permeability, foldability, and then things like non-flammability, chemical inert, vacuum capabilities, and various aspects like that. You can see what has to be looked at between the external space environment and the internal safety aspects. So this just gives an overview of that. This is a breakdown here, this table of the materials that we looked at, and it is basically taking the various layers between the external and the internal, and then looking at that to see the number of layers that we had, the areal density, and then looking at the total mass. So you can see even from that we got a figure of about 7 tons for the choice of materials that were there. And that's taking into account the basic aspects of the radiation protection, what is being used for the minimum thickness, and what is there for functionality of those materials. So these are some of the figures that we came to in the use of those materials. And you can see certainly we're taking a shell area of that kind of area. It was 420 meters squared. And then, of course, you build up the figure then based on that for the total mass. And then the shell mass then was around 7 tons, as you can see. But it takes the various aspects of the areal density, and it shows you directly the influence of materials design choices on the higher load and the structural masses that are there as part of the mass budget. Some of the challenges, of course, on the external ones, we're aware the external challenges are the dust, what it means for the dust in relation to contact with the materials, the non-conductive external layers. Of course, that may be an issue. Certainly on the Apollo, it was an issue where you get a sticking of the dust onto the surface. You can have ESD risks. You can have increased dust impact, that type of thing. Also, externally, you have issues of MMOD. Of course, you have to have things like the protection, and certainly the foam is used then for protection of that. Separation foams can expand, and that's certainly something that has to be borne in mind at the cryogenic temperatures. Some of the other challenges going forward for the restraint layers, certainly the the interconnectivity of the interfaces between the woven structures and the rigid structures. So that's something where we have to look at, say, the leak capacity of that. What do we do for materials choices in those interfaces? If we have to have a glue, if we have to have an epoxy, or if we have to have something that holds in place where it ensures the leak tightness of these interfaces. And then how do we actually qualify that? What does it mean that we have a rigid structure or in cooperation with a weave structure? How are we ensuring the weave structure is homogeneous? How are we ensuring that it is leak tight? And how we ensure that the quality of the weave is actually sustaining the environments that are there? So they're all aspects that need to be looked at when considering choice, when considering materials, and indeed longer future missions. What happens with respect to exposure? Going on, the bladder material, of course, we talked about that. You have issues of puncture, you have issues of flammability and oxygen, and also moisture, and what it means with respect to, for instance, the complex nature of the bladder with the loads, the increased oxygen. For instance, if you have crew, it may need to be susceptible to higher oxygen contents, 30 or 40% oxygen in some cases. So it cannot be a flammable material. And then you have to have issues where it must maintain cleanliness, for instance, fungus resistant and contamination, clean material for the internal structure of that. So for the bladder material, there are certainly aspects that need to be looked at. This is just an overview here on some of the glass aspects and that we looked at. I can go quickly through that. It's just some of the issues with respect to the structural issues, with respect to the thickness, and of course the radiation is another issue on that. One of the other challenges that was mentioned, of course, is the technical challenge with respect to leakage, with respect to damage, and with respect to repair. So one of the issues here is looking at, for instance, collision with respect to a micrometeorite, with respect to impact, and what does it mean for materials choice? Do we have something, for instance, that can be used which is self-healing, for instance, a rubber or an organic material that self-heals? If that is the case, what is the range for the self-healing? How easily is it done, and what is the capability of that? They're all aspects that need to be looked at. And then if it is not, then how do we choose a material, for instance, where we look at hypervelocity impacts and what that means with respect to safety and the aspects of the materials, and also the materials functionality and how it sustains those impacts going forward. So these are all aspects that need to be looked at. For instance, in the glass that you see here on the left, with respect to fracture, and then with respect to the woven materials and the fabric materials for design choices. So certainly one of the issues there would be repair and replacement, and how that can be done. This is just a quick overview here of some of the examples of the hazards. And so, for instance, internal in any crewed environment, we have issues of fire, sharp edges, touch temperatures, off-gassing, toxicity, shatterable materials, dust. All of those aspects have to be taken into account. They all constitute safety hazards, and they all constitute issues that have to be looked at and taken into account for materials design. So these are all aspects on top of the lunar environment aspects that need to be included when looking at materials and materials choices. Going on, of course, yeah, there are examples of some of the materials with respect to forbidden materials and what is used, and then an overview from the ISS for VOCs, volatile organic compounds, and these are mainly restricted because of systematic and system impacts on ETLIS systems. So where you have these alcohols that are being used, certainly that imposes a system impact on some of the life environmental systems, and then that has to be taken into account, or at least substantially restricted for their use. The dust environment, of course, yeah, this is one of the main aspects that we consider for habitable structures and what is there. The dust is, of course, it can be sharp. It can be various particle sizes from half a micron to maybe 100 microns, depending on the environment. So they are all aspects that we need to take into account for qualification of materials. And how do we do that? Okay, we need to test like everything else. So in ESTEC, in ESO, we have a facility, which is the dust adhesion facility, where we look at exposing materials, mechanisms, and different other systems to dust environment. And we look at dust adhesion, we look at materials interaction, and we look at how it performs in relation to that environment. Certainly for a habitat structure and a lunar habitat structure, certainly of a mission of several years, this is something that needs to be taken into account. For instance, electrostatics, do you do something like that? Or do you have something where you can have a self-cleaning effect, or something where you can have a mechanism to physically clean the dust off the surface? So these are some of the aspects that need to be looked at. Certainly for a habitable structure, it is a long-term structure on board the environment of a lunar aspect, and it's certainly something that has to be chosen with care. Okay, for the end, just to conclude, for sure, given what we have and given what I've shown for the materials aspects, there is a trade-off between the functionality of the materials, between the weight and the environment and what is there. So there are certainly aspects that need to be looked at with respect to the choice, with respect to the weight, with respect to the repair and the replacement, and what is there. And while there are limits in the choices, there are many viable and working options. As I say, there are materials that are there that can work and that are functional under the environment of the lunar aspect with respect to temperature, radiation, thermal control, and also functionality. There is heritage, as I say, on the American side with the Bigelow and some of the NASA developments that have been there, and certainly also on the European side, we have structures and we have developments and previous experience of habitable structures and what has been used. So certainly going forward with respect to the new missions and with respect to future and exciting challenges, certainly this is something we look forward to, and it's certainly something where materials will form a core aspect of that. And certainly going forward, the knowledge of materials and what is there will certainly be a central role to what is chosen and the design aspects of that. So certainly it is something where we will be busy in the future, and certainly new challenges and new opportunities await in the area of materials. So that's it. That's my talk. Thank you to everybody for listening today, and I welcome any questions you may have.
Okay, well, thank you, Cathal, for a fantastic workshop presentation today. We've been really looking forward to this one. Conscious of time, so in terms of the Q&A, I've just got one question for you. I think you touched on it in the Bigelow slide, but I was wondering if you could elaborate on the benefits and drawbacks of using semi-rigid materials for lunar habitats.
Sure. Thank you, James. Certainly with respect to the semi-rigid materials, of course, the main aspect on that and the main saver for that is the issue of the weight and the mass saving. So where you have, for instance, rigid structures that will, of course, be radiation protective and what can be used for radiation, the lightweight materials and the multi-layer materials certainly fulfill that function and certainly can do that to the same degree with sometimes an external helping, be it regolith or be it an external shielding, that you can still maintain the functionality over a long-term mission and still maintain the weight benefits of the lighter structures.
That's great. That's great. Well, thank you. And yeah, thanks again for that workshop presentation today. And before we jump off, I just want to touch on a few things I mentioned at the start. if this workshop has catalyzed any creativity or creative juices in our audience, then it'd be great if they could get involved. We've got a number of activities on the DoraHacks website. The first one being the Starship Use Cases Hackathon, which is live now, and the submission portal is still open. So there's a prize pool of $100K US for that, and a number of use cases for people to get involved in. So any teams that want to get stuck into that, that's still live. And we've also got a Space Resources and Exploration Grant Program, which is a long-term fixture on our platform, which provides support to innovators in the field of space technology. So whether you're an individual or a team working in this area, specifically if there have been things brought up in today's workshop, do get involved in that to get your hands on a grant to further development, because that's one of the things we're really keen on promoting here at DoraHacks, is finding those innovators in the early stages of development and help them expand on their projects.
Thank you, James, again for your help and assistance on this, and certainly it was good for me to talk and have the exposure to the DoraHacks platform today, and any interests or questions, of course, can be fed from you, James, or I can get from Sibai, and we can work on those going forward. If there is additional interest from people, or if they have in general any questions, we can certainly share any information or have a discussion at another time. So that's always welcome.
Great stuff. Yeah, well, thanks so much again for jumping on. Any questions from the audience, whether you're listening live or catching up on YouTube, leave them in the comments below and we'll pass them over to Cathal. And yeah, it's an exciting time. Do follow our links that we put in the group, and follow us on social media, as we do have other workshops similar to this in the field of space technology and other frontier techs. So keep in touch at DoraHacks on Twitter or YouTube or wherever you like to follow. And thanks again, Cathal.
Thank you very much, James, and thank you to the audience for today.
Thank you, everyone. Thanks for tuning in. Bye-bye.
Bye-bye.